Okay. So let me draw the following picture of x0p. So when we think about overconvergent forms, we can think about them as two ways. We can think about them as sections of, say, the modular curve x01 away from some small disks around the supersingular points. But similarly, we can think about them as functions or sections on x0p where we've pulled back from x01 to x0p using the canonical subgroup. So we might have a picture that looks a little like this. So this is x0p. Here we have one cusp infinity. Here we have one cusp 0. This is the ordinary locus. Now there's also some ordinary locus up the other side. This is the ordinary locus where the subgroup corresponds to the canonical subgroup, and this is the part of the ordinary locus in which it doesn't. And here in the middle is the supersingular locus, and we can define overconvergent forms if we take certain, if we somehow extend this region far enough into the supersingular locus. In fact, anywhere into the supersingular locus is good enough, but we can do further or less far depending on this radius of convergence. But one picture that we have on x0p that we don't have on x01 is that x0p has a nice involution called the Fricker involution. And it's easy to describe on a pair E and a subgroup. It sends it to E quotient out by that subgroup, and then you get a subgroup of order P by taking EP quotient out by P. And you can check that this is an involution. And you can also see what happens geometrically. It takes ordinary locus to the ordinary locus, but it swaps both of these ordinary locuses. It takes infinity to 0 and 0 to infinity. And in particular, it also somehow inverts the supersingular locus. You can also see what it does as far as the canonical subgroup goes. And in fact, suppose we take an R, say in the range 1 on 1 plus P and P on 1 plus P. Then it takes this region, well, so let's do this. And let's also now suppose that R is big enough, particularly if R is bigger than a half. Then there's an intersection between the overconvergent modular functions of radius R and the Fricker involution applied to these functions. So on the one hand, you should think of this on the left-hand side as being sections that go as far as this disk, so sections in this region here. On the other hand, if you apply the Fricker involution, well, if these disks are deep enough, you then get sections of the other side, and the intersection of these two spaces are now, so there are functions in here and functions in here. They're only going to be well defined somehow on these small annuli. So in other words, value have functions, maybe I'll put it this way, so functions that will be defined on these small little annuli inside the supersingular region. But that allows us, in fact, to define a pairing. So if R is at least a half, and let me now suppose the weight is equal to 0, this is interesting to think about in other weights as well, there's a pairing between overconvergent modular forms of deep enough radius with itself. So what you do is you take F, and then you take G, you apply the Fricker involution to G, and then you want to pair these together. So you take F and G, and what do? You take WG, and then you multiply it by the derivative F, and then you take the integral. All right. So taking the derivative is an operation that is acceptable because we actually have a function, and the derivative is naturally somehow a form of weight 2. These two are both defined on this little annuli in the middle. You might ask, what does it make, does it make sense to talk about an integral in this space? But this is really not an analytic thing, but it's really a kind of algebraic construction. I could write it in this form instead. And you should interpret this as follows. We really just have that these regions are given by annuli. And if you think about functions on annuli, and let me not be too careful with the radius of convergence, then you can think about defining the integral of an annuli as just being equal to, say, a minus 1. Right? You somehow, if you literally had, say, a function on an annuli in the complex plane, you could just integrate it. And of course, you can integrate it term by term, and you would exactly get this, even if it's not defined outside these regions. Now, of course, there's a choice of how you integrate it, which is you integrate it left or you integrate it to the right, which somehow is, if you're doing it, the inside or the outside. And so this infinity here is just giving you a direction. You're thinking towards the infinite cusp rather than the zero cusp. I mean, it would just change the sign if you did it in the other direction. So you have some nice pairing. And a fact that you can compute about this pairing is that this pairing is actually Hecker equivariant. So, in other words, UFG is equal to FUG, and TLFG is equal to FTLG. So again, we're trying to study this operator U, and we're trying to understand its spectrum, at least for various radii of convergence. And so we have the following two facts. So if R is sufficiently big, so in particular if R is bigger than 1 on 1 plus P, then the kernel of U is actually trivial. So that's somehow a good thing to have if we wanted to have a spectral expansion. And then similarly in this range, if we somehow also even know that R is bigger or equal to a half, then on this space, the operator U is self-adjoint with respect to this pairing. So it's actually an interesting question to understand what we actually get from the fact that the kernel is trivial and U is self-adjoint. So if you think about a finite dimensional vector space and you have an operator that's self-adjoint, well, normally you think self-adjoint, you think a Hermitian matrix, and you know it's diagonalizable. So this looks interesting. But again, you realize self-adjoint in this context really just means it's symmetric with respect to some basis. And if you take symmetric matrices over C, that's not very interesting. In fact, any finite matrix is conjugate to a symmetric matrix over C. So it seems perhaps it's less interesting. On the other hand, it's not so hard to show that this is actually a condition, but it leads to just a problem, which is just a problem in linear algebra, which is take an infinite by infinite matrix over ZP that's compact. So you can think of this as just a matrix which reduced mod P to the n has only finitely many entries. And so let me give the matrix a name. Take M in this matrix, and you suppose two facts. Suppose that one, say the kernel of M is trivial, and two, M is symmetric. And then the question is, what can you deduce about M? So that's a perhaps slightly vague question, but it's still an interesting one. If you can say anything non-trivial, you can deduce formal properties of this operator U without having to do any geometry, but maybe just by doing linear algebra. This is the kind of question that turns up. Now let me move on to congruences. I explained a little about this in the last talk. So recall that we conjecturally have a spectral expansion, somehow given an F in over convergent forms. We expect that F is equal to the sum alpha I times phi I from I equals 1 to infinity for these eigenforms, which have slope, or rather, which have u vi equals lambda I vi. So this is the hope. So now we can try and connect this, for example, to the pairing. Well, I only really defined the pairing when k is equal to 0. And again, we're trying to hope that this pairing puts us in a situation where this u looks a little bit like an operator on a Hilbert space. And this pairing, since it's equivariant with respect to the operators, we might ask for the following upgrade. The upgrade on the spectral conjecture. Whoops. Upgrade. We have the following conjecture, namely that f is not only equal to a sum of this form, but that we can explicitly compute it simply by taking the pairing of f with these eigenforms and dividing by normalizing them so that they have norm 1. So this would exactly be true if you have an operator in a Hilbert space that's self-adjoint. So this is, I should generally say this conjecture about spectral expansions is due to Gouveia and Mazur. This upgrade is actually in the special case where n is equal to 1 and p is equal to 2 and the weight is equal to 0. This is, in this case, it's a theorem of David Loeffler. So that's some evidence that this may be true in general. It's a very specific case, and it uses the fact that in these low prime and low level situation, the curves involved are really curves of genus 0, which means that the spaces of over convergent forms are spaces on a disk, and it's a lot easier to work explicitly with functions on a disk than it is to work with functions on some Swiss cheese. Okay. All right. So again, I referred to this way of thinking about or hoping to decompose functions right at the very beginning in order to, say, deduce results about congruences in some very explicit way. But again, even still using the asymptotic expansion, one can still say some things. So I want to do some specific examples. So first I want to do the example again of J, which I've talked about before. So if we take J, well, first we want to apply U to it to turn it into a holomorphic p-adic modular form to get rid of the cuspidic 0. So using Hitter's theorem, we can write it as its ordinary projection plus the other part of the space. And what we know about that space is, at least I'll put quotes in here because this is an asymptotic rather than exact expression, unless p is equal to 2, in which case it is exact. A sum here again of these eigenforms by I, where here that these are non-ordinary, so that corresponds to these eigenvalues being strictly less than 1. Okay. So what one deduces from this is the following: congruences for the coefficients of J. So on the one hand, this is given by a finite sum of eigenforms. And you know the dimension only depends on, well, the dimension is easy to compute. It's related to the ordinary space in weight p minus 1. So its dimension is essentially p minus 1 on 12. So you have, roughly, so you have these eigenforms here. And what you deduce, therefore, is if you compute, if you iterate u on this expression, you would deduce, for example, that c, p to the n times k, where c are the coefficients of j, well, on the one hand, you get some finite sum corresponding to the eigenforms. When you apply this u operator, you still have the same eigenforms. But then this expression here is somehow vanishing and going to 0 at some fast rate. How fast a rate does it go to it? Well, it just corresponds to what the biggest eigenvalue is. So the biggest eigenvalue, it can't be as big as 1, has to be smaller than 1. So the error term is then p to the power of n times a constant c, where here c will literally be equal to the minimum of the valuation of these eigenvalues at least for the eigenvalues that have valuation strictly bigger than 0, because the ordinary forms have been excised. And what you can do is you can compute a few examples, and if you compute a few examples, what you'll find is that this error term, I mean, this C is just some number. I mean, it has to be rational, but it could be arbitrarily small. But you see, just if you compute it, well, you will see, I guess I haven't actually literally computed it myself, that the error terms will look like actually O of p to the n, rather than OP to the nc for some small c. So I wanted to just prove that, so I want to prove the following lemma, is that actually C is at least 1. So in fact, for all n, for all primes, you get a congruence for these coefficients of j as a finite number of eigenforms modulo something really of size p to the n. So of course, in any specific example, you can compute enough of the Fredholm power series of U to compute the first few slopes, but we'd like some way of proving that there really aren't any slopes between 0 or 1. So there's no a priori reason why that should be true. So before I prove that lemma, maybe I should also give a second example, which is basically in some sense of the same flavor. So again, instead of j, let me choose e to inverse, which, as I said before, is q to the minus 1 on 24, the sum of the partitions of n times q to the n. And again, by the same computation, you can write u of e to inverse as its ordinary projection, EP of u e to inverse, plus some sum, again, alpha I, phi I. And again, this will correspond to a congruence. Let me write it like this. P star of p to the n times k will be, again, a finite fixed sum of eigenforms plus an error term OP to the nc. So I'm writing P star here just because the annoyance of this 1 on 24 means you get a shift in some kind of way that involves something plus something over 24. It's a sort of elementary to translate what you get, but it's not something I'm going to do specifically. And again, here, well, here for small primes, it turns out there's nothing ordinary, and the small slope is some 1, 1, 2, or 3, depending on how P is 3, 5, or, sorry, 5, 7, or 11. Again, because of the shift, this is somehow a complete triviality if P is 2 or 3, because in fact, if you apply U, you simply get 0, and you get no real information at all. But for big primes P, again, here's the following lemma, is that C is bigger or equal to 1. So in other words, the congruences you get for the partition function are true modulo really O P to the n when you do it n times. Okay. So how do we prove these? Well, let me start with the case of J. So we need to prove, the question is, does there exist a phi which is over-convergent of weight 0, level 1, and the radius is somehow not so important. Does there exist such that if you apply U to it, the eigenvalue has the slope between 1 and 0? So in other words, the valuation, it's smaller than a unit, but it's somehow, can it be strictly bigger than P? So that's the question, and the lemma basically says that this doesn't exist. So now you have to use something a little bit more, namely you have to use the fact proved by Coleman, which is in some sense the point of what Coleman did, was that these eigenforms actually deform in families. And from the existence of this, so if phi exists, then there also exists, in fact, a classical modular form, modular form F of high weight, but still weight congruent to 0 modulo P minus 1. And it has level 1, and such that the slope of F, so in other words, the slope, well, rather in terms of, put it this way, the valuation of AP is equal to the valuation of lambda. All right. So it turns out that this AP actually tells you quite a lot about the Gower representation associated to F. A well-known fact, for example, is if AP was a unit, then the corresponding Gower representation is ordinary. And so even if you then restrict the corresponding Gower representation mod P, you also get something ordinary. But it's a little more complicated to understand what the corresponding local Gower representation is when AP is no longer a unit. But in fact, it is the following theorem of Buzzard and G that actually implies in this situation you know exactly what the corresponding Gower representation is. It actually you deduce that the representation mod P of F, which is therefore by congruence equal to this representation, restricted to dP, is equal to, well, it's something very explicit. It's the induction from the quadratic extension of this tame character of level 2 to the power of P minus 2. Okay, so it's irreducible. If P is 3, for example, then that would look like what you would get from the mod 3 representation of a supersingular elliptic curve. All right, so we have this representation in some weight that's congruent to 0 mod P minus 1, which has this particular shape. So in particular, rho bar actually has to be globally irreducible as well, because it's locally irreducible. And if you look at this and you take an appropriate twist, and then you apply Sayre's conjecture, well, even really just the weight reduction of Sayre's conjecture, you deduce the following. If you twist by the square of the cyclotomic character, you get this is modular of level 1, and weight 4. Okay. So if you have something of slope between 0 and 1, and you look at the corresponding representation rho bar, by Sayre's conjecture, you can trace where it actually has to turn up, and it has to be a modular form of level 1 and weight 4. Well, we all know that there aren't any such modular forms of weight 4 that are cuspidal, and since rho bar is irreducible, that says that this is a contradiction, and therefore, that's the proof of the lemma. So nothing of slope in the range 0 and 1. In fact, the argument in the case of partitions is pretty much the same. So let me say how one does it here. So in the case of the partitions, now you have some eigenform, which is in the space of forms of weight minus a half. Well, let me call it level 1. I mean, it's eta inverse, which is in some sense of level 1. And you assume that somehow the valuation of lambda is between 1 and 0. So what you can do is, using this form, by the Shimura correspondence, you can get an overconvergent modular form of integral weight, which is now weight, well, 2 times minus a half minus 1, which is minus 2, in gamma 0, 1, which has the same slope. Yes. I won't put the level, then has the same slope. So again, you can compare modular forms of half integer weight to forms of integer weight using this correspondence. If you're only interested in comparing eigenforms and the slope, there's an easy way of doing it, which is a kind of soft proof just using the trace formula. Now, of course, in real life, you might want to get extra information concerning L values, but if you're just interested in slopes, it's not so hard. But you can actually check exactly where it should be. It should have level gamma 0, 6. Well, that's after you've twisted by some character of order 12. Moreover, you can actually check it has to be nu at 2 and 3, and the U2 eigenvalue has to be 2 to the minus 2, and the U3 eigenvalue has to be 3 to the minus 2. So of course, we're assuming P is not 2 or 3. So you get some particular form. Again, it has half integer slope. Again, you can use Buzzard G to produce some rho bar. And what do you end up with? Well, you end up with, again, getting some rho bar, which in this case will have to have weight 6. It will have to have level gamma 0, 6. And again, it will have to be nu 2, 3. It will have to be nu. Now, you can just check this space. Well, it turns out this space is one-dimensional, which is maybe not so good. On the other hand, if you check this one-dimensional space, and you check the U2 eigenvalues, well, it's equal to 2 squared, but U3 is equal to minus 3 squared. And so again, these two things are incompatible, and again, you will see that it can't exist. All right. Of course, in general, at general weights and general levels, there's no reason to expect that there might not be something of slope between 0 and 1, and moreover, you can explicitly construct examples where there exist things of that slope. So for general congruences, you only get a linear growth of congruences up to, say, some fixed constants. Okay. So for the remainder of the time, what I want to talk about is the following problem. So a lot of these ways of thinking end up leading us to a decomposition of various forms into these overconvergent eigenforms. So just as a very basic question, you might want to understand something about the p-adic analysis of overconvergent eigenforms. Convergent eigenforms. So we're in a situation where we fixed an n, we fixed a level, and we fixed a prime, and then we have this countable collection of eigenforms. So Don Blasius once asked me, I mean, he sort of said, this is somehow analogous to a following situation, namely if you fix a level and then you ask for some infinite sequence of forms, how could you get it? Well, you could look at the mass forms. Again, so here these are eigenforms for some operator u. Here you have some eigenforms for some Laplacian, and you have some countable sequence if you stick to the cuspidal spectrum, and they have some interesting analytic behavior. Are they in any way analogous to these finite slope objects? And part of what I wanted to talk about is that they really seem to be the case. So we have these objects here, and also if you fix a level, you say have mass forms. Again, these are just things of weight 0 that are eigenforms of Laplacian. I want to give them different names. Well, that's a different letter. So what's some fact about mass forms that you might want to study, and how can you compare them to, say, these overconvergent forms? Well, here's a fact about mass forms. So these mass forms, they come with some eigenvalue of the Laplacian. And for example, you could count how many of these there are, the number of I, such that the Laplacian eigenvalue, I'll call it lambda I, of phi I is less than t. So there's some countable sequence. As you go up, you get more and more of these eigenforms. And then Weil's law gives you a formula for this. Namely, this number is approximately the volume of the corresponding modular curve divided by 4 pi times t. That's an asymptotic formula. All right, so what might you ask then, say, for finite slope eigenforms? Well, again, you could now have nt, and you could ask for the number of I, such that the valuation of this eigenvalue is at most t. All right. Now, if you start to compute this, you actually see it really depends on p in some way, which it doesn't on this case. On the other hand, you have the following conjecture, which I'll call the p-adic Weil law. I don't know if I should put Weil's law or not. And that says the following, or maybe I should put a p here, is that this is now proportional to something what looks quite similar. Now instead of the volume of x, you have the volume of x 0p, which you might think is reasonable because these are also sections of x 0p. And what else does it look like? Well, otherwise it looks like divided by 4 pi times t. So hopefully this justifies that the analogy is not somehow a complete accident. So what's known about this? So it follows from results of 1 that you have the correct upper bound and you have the correct lower bound. Well, okay, that sounds really good. But the correct lower bound is up to a constant. Up to a constant scalar, I should say, of course. So you know that there are at most this many, and you know there are at most a constant times that many. Okay. And again, in some special cases, p is 2, n equals 1, and level weight equals 0, then you know everything. So then you're in good shape. But again, that's reducing to computations that you can do because you're in genus 0. Okay, well then you can start to ask other questions that you might also ask for Weil's law. So there's a subject that was sort of initiated by Sarnak, which one might call, well, usually goes by the name arithmetic, well, quantum chaos, or arithmetic quantum unique ergodicity. And this is concerned somehow with the following problems. If you take these mass forms phi I, you can ask questions, for example, about the distribution of mass. In other words, if you take some kind of classical limit where you're taking the eigenvalue to be bigger and bigger, do these eigenforms somehow, are they somehow really big near a single point I and kind of very small everywhere else? Or is their mass somehow distributed everywhere? This you can somehow answer. You can also ask questions of, say, what does the 0 set look like? You get various nodal domains, and you can ask something about these things. But certainly just as kind of an analytical sequence of objects, they're very interesting, and it's very natural to try and study them and to understand what they do. I mean, why is it interesting to understand them? Well, if you generally have a function, you might want to expand it out into some expansion in terms of eigenvalues, and then if you know some property about the eigenvalues, you can perhaps deduce something about the original functions. So somehow what I would propose is that it might also be interesting to study the corresponding questions, or at least related questions, for these overconvergent eigenforms. Since in the case of Weil's law, it seems you get something very similar, it might be interesting to ask, what does the distribution of these eigenforms look like in terms of functions? What do their zeros look like? What happens when you take these eigenforms and let the eigenvalue, well, the eigenvalue of u now tend to 0? So of course, this is really a kind of, not just arithmetic, it's p-adic arithmetic. So I really should put p now p-adic. And these are really overconvergent. So this is, I want to christen this subject. And as the name suggests, there's some very confusing and surprising phenomenon that, in fact, my students have computed and observed, and I have absolutely no idea why some of these extraordinary patterns are occurring. And in the 2 days that my students had to think about them, they couldn't prove them, but I couldn't prove them in several months, so maybe that's not so bad. And what they're going to be talking about is something about what is the behavior of these eigenforms, and just show you some remarkable properties that hopefully one should try to understand. Okay. Well, that's probably a good point to stop.